Hello friends, I'm Nikita and you are watching Prepare for GATE. Analog electronics is one of the major subjects which contains around 5 to 10 marks questions every year in GATE examination paper. Moving on with the syllabus of analog electronics, which varies from BJT, diodes, MOSFETs, and their applications. Today, the topic to be discussed will be small signal equivalent circuits of diodes, simple diode, clipping, clamping, rectifier, voltage reference circuits, power supplies, ripple removal, and regulation. A semiconductor diode is an electrical device which comprises of two regions, one P region and other N region, which conjointly form a PN junction. The diode works as short circuit when the device is forward biased and open circuit when the device is reverse biased in ideal conditions. However, in practical conditions, there is always some threshold voltage or inside the diode, which is the built-in voltage, which only after overcoming that amount of voltage, the diode starts conducting. Here, you can look the basic form of a PN junction, P and N region. They are joined together, and the diode behaves like a short circuit when the current is greater than 0 and it is in forward direction, and which behaves as open circuit when voltage is less than 0 and current is 0. Now looking at the characteristics of the diode, in ideal condition we will find that in reverse bias condition the current through the diode is 0, whereas in forward bias the current goes infinite at V0. However, in non-ideal conditions, more in the practical cases, we will find that when the diode is forward biased, it will have some amount of diode voltage that needs to be overcome before being conducted in forward bias direction. The threshold voltage is 0.7 volts for a non-ideal diode. In the reverse direction, we will see that it does have some saturation current, which is in an amount of 10 to the power minus 12 to 10 to the power minus 15 amperes. However, when the reverse bias reaches the Zener voltage minus VZK, K is for the knee current and Z is for the Zener. When it reaches beyond Zener voltage, you will observe that there won't be any increase in reverse bias voltage across the PN junction. However, the current will be increasing dramatically. So you can see that how there is a large flow of charge carriers after the Zener voltage is obtained, and there is no further increase in Zener voltage. So we have one reverse condition and we have one breakdown condition. In Zener diode operating in reverse breakdown region is termed as Zener diode. In reverse bias mode, when the input voltage equals to the Zener breakdown voltage, the diode current rises exponentially, which is termed as the knee current. For Vz is equals to Vz0 plus Iz into Rz. Looking at the characteristics of a Zener diode, we can see that in the forward direction it behaves just like a normal diode, whereas in reverse bias condition it behaves similar to the normal diode, and after the Zener voltage is achieved, the current through it rises exponentially in the negative direction, whereas the voltage across the device remains constant. Thus, it requires to maintain a constant potential across a device with increasing currents. Once the general voltage is achieved, no further increase in voltage takes place across the device. Now, one more thing I need to point out over here, that often people are getting confused between the positive side of the diode and the negative side. And I must tell you that the point where there is a bar with where there is a limiter bar, then this is the plus sign and this is the minus sign. You can say it's the cathode and this one is the anode. With change in temperature, Zener diode changes, and the accurate measurement of which can be found by relation Tc is equals to del Vz upon Vz, T2 minus T1 into 100, where Tc is the Curie temperature. Now, as we have already, there are many models that we'll come across in calculating the various potential and the diode current passing through the circuit, for which the first one is the ideal diode characteristic, for which the potential across the diode is 0 and current will rise infinitely across, and that will be dependent on the external circuitry of the device. In constant current voltage drop, we'll see that from these graphs that a constant potential of 0.7 volts is present near the diode, and after subtracting that potential from the actual circuit voltage, and dividing it by our resistance, we can get our current. Let's move to the next model. We'll see a small signal approximation of semiconductor diode, which is the most accurate one that we comes across. Now, if you can see that there are two diodes, one is a DC voltage. There is only one diode, and however two signals. One is a VDT, an AC signal, and other is a DC signal, which is passing through the diode. Now, if we consider a small DC signal with AC signal are passing through a diode, and to determine a DC bias point, the diode is modeled by a resistance equal to the inverse of the slope of this tangent passing through the ID line, ID and VD line. A DC voltage, a VD, and a time varying VDT assumed to have a triangular waveform superimposed on the DC voltage VD. In absence of VDT, the diode will conduct ID, given by ID is equals to IDS e to the power VD slash VT. VD is this voltage. Because of it, the diode current will be dependent on the initial voltage. Diode current is equals to saturation current, reverse saturation current into e to the power VD slash VT. Where VDT is applied, then VDT is VT plus VDT. That means both the signals are present. Now, we add these signals in the exponential part, in the power part of the exponential signal, and we get this that you can see the time varying diode current. If we add the voltage in the power of the exponential function, then on doing some mathematical calculation, the final result will be ID is equals to e to the power V dt. Dt, this is the time varying diode voltage divided by the threshold voltage, and this is the main approximation I would like to point out at this point. That remember that if VDT, that is the time varying voltage, is less than VT, threshold voltage is less than 1, then one must consider this small exponential approximation, that is 1 plus VD over VT into IT. Thus it means that we ignore the time varying exponential function and the VD, that is the DC. This is the DC voltage. This is not, my friends, any time varying voltage. It is the DC voltage. Now VD slash VDT over VT into ID. So this makes the time varying diode current a constant diode current, and it will remain the same throughout. Moving on with a small signal approximation, we can find that Vt is equals to 25 millivolts. If you compare it with the last equation, ID is equals to 1 plus Vd slash Vt, you will find, and then substitute it's just the same. Now the diode conductance will be the differentiation of the ID current with respect to Vt current, and you will see that the diode current is equals to over Vd voltage. So Vd voltage. If we consider it over differentiative over Vd voltage, then it comes out to be ID over Vt. And the inverse of the small signal conductance of diode small signal resistance will be reverse of the conductance, which is Vt over It. Look at this small table. For DC, RD will be equals to Vt over It, defined as a point on the characteristics. For AC or dynamic, RD is equals to Vt over Id. Vt is the threshold voltage, 26 millivolt over It, defined by the tangent light at the Q point. So it is not dependent on the AC voltage. Moreover, it is dependent on the threshold, constant threshold voltage divided by the ID. Now, for our average, we get the difference in Vt over difference in ID. It forms almost a straight line. So the approximation will be like a slope. Moving to the next point, having considered about the various and talked about the various characteristics and the model of a diode, we will move into its biasing. Here I would like to tell you some basic points, considering that you have already know about the PN junction. If you don't know about the PN junction much, then kindly refer to my slide on electronics devices, where I have briefly talked about the inside mechanism of a PN junction diode, and which will be very helpful in learning about the inside mechanism of the PN junction diode. Now, if you look this in the forward direction, this is actually the internal mechanism of a PN junction diode. It consists of two charge carriers. One is the majority charge carrier and other is the minority charge carrier. If you look at in the P side region, you will see that this region is doped with a P-type semiconductor. A P-type semiconductor we have already talked about. It is a type of semiconductor which have 5 valence electrons, right? No, I think you must be thinking that she's talking wrong, but yeah, I'm wrong in that sense that it does not contain 5 electrons. It contains 3 electrons in its valence shell. Thus it obtains 1 electron from the silicon present in the diode as a majority carrier, and turns itself into a negative acceptor ion, or into a negative ion or an acceptor ion, and other as a positive ion. So it is the majority charge carriers are the positive ions with negative acceptors. On the other hand, in the N-type region, it is mostly the opposite of the P-type region. Here we doped it with a with electrons that have 5 valence shell, 5 valence electrons in its valence shell. Thus, they donate one electron, making themselves as donor ions and other as the negative. So they are positive charge and the other is negative charge. So you will find that the negative charge is the majority charge carrier in N-type and the positive charge is a majority charge carrier in the P-type. In the forward direction, we'll see that the majority carriers move from the plus side of the region to the minus side. And in as we have talked earlier, that in forward direction, the depletion region shrinks. It doesn't expand, but it shrinks. And the potential developed across this depletion region is subtracted from the actual circuit diode region. So this was the major analysis of a PN junction diode. Now moving on, explaining that in forward direction, we'll see that the diode is in on condition when the P side of the diode is conducted to the positive terminal and N side of the diode is connected to the negative terminal. The application of the forward bias pressurizes the minority carrier present near the ions to merge with the ions and reduces the width of the depletion region. Both the ions merge, both the plus and the minus merge to form a permanent depletion region, a reduced depletion region. Now we have already talked about the diode current, that diode current is equals to I of S e to the power Vt minus Vt, whereas the saturation. Okay, where Is is the reverse saturation current. For appreciable current I in the forward direction can be approximated by the exponential relation I is equals to Is e to the power V slash Vt. In the logarithmic form, we can say that V is equals to Vt natural log of I over I. Now, if we have two different diodes with the two different diode current and two different potentials, then we can calculate the difference between the two diode voltage V1 minus V2 or V2 minus V1 by this formula, which is 2.3 Vt log of, not natural log, but the log to the base 10 logarithmic log is equal into I2 by I1. Okay. At a given diode current, the voltage drop across the diode decreases by approximately. The voltage drop across diode decreases. Remember, it's the voltage drop, not the diode current. If we get confused oftentimes because the diode current or the reverse saturation current, it doubles for every 10 degree rise in temperature, but the diode voltage decreases for every 2 millivolt for 1 degree, for every 1 degree Celsius change. Okay, it decreases. Remember that. Now, talking about the reverse bias conditions, we can say that in reverse bias, as we have seen the IV characteristic in reverse bias direction, that before Zener voltage or the knee current flowing, it behaves in the current diode. The current passing through the diode is a reverse saturation current, which is often in the order of 10 to the power minus 14 to 10 to the power minus 16. This range varies, and it could be minus 10 to the power minus 12 also. So do not take it fixed. And the reverse saturation current, as I have already talked about, it doubles for every 5 degrees Celsius. Reverse saturation current doubles for every 5 degrees Celsius, and reverse current doubles for every 10 degree rise in temperature. Now, moving on the other characteristics of the diode. One more thing I would like to tell you over this point of time, that the formula, how to calculate it. If you can see that if IC2, you need to calculate, okay, which is equals to IC1, that was the earlier, which is 2 to the power T2 minus 1 divided by this formula you can actually calculate the reverse saturation current. Now we talk about the other transition and other diffusion capacitance. These are the other parameters of the diode itself. In reverse bias condition we have transition or depletion region capacitance, and in forward bias region we have diffusion or storage capacitance. In reverse bias, with the increase in voltage, the width of the depletion region increases. The depletion capacitance decreases. So remember, transition capacitance or depletion capacitance is in reverse bias condition, and diffusion capacitance, the majority carriers are diffusing into the other region, into N region, okay, or the majority carrier in P region are diffusing, okay, remember, are diffusing, they won't be diffusing, right? So let's just forget that. So in forward direction we have depletion or transition capacitance, and in forward direction we have storage and diffusion capacitance, and in reverse bias we have transition or depletion capacitance, okay. So moving on, in the reverse bias, with increase in voltage, the width of the depletion region increases. The depletion capacitance decreases because it is the formula that C is equals to epsilon of A, sorry about the A, divided by, sometimes my writing is crooked. So you can see that as the depletion region increases, the capacitance decreases, as the width of the capacitance is directly proportional to the voltage. Okay, this is directly proportional to the voltage because earlier we have seen that V square is equals to 1 by 2 Q by epsilon, okay, N A N D over plus N D W square, right? Okay, W square. So by this formula we know, oh sorry, this is not the square, remove this square. I have an eraser. Oh, it has erased everything. Oh, it will be erasing everything. I'm not doing it again. So yeah, the voltage is equals to 1 over, is it voltage? Oh yes, it is voltage square is equal, this is not this, this is not the square. Okay, now moving on. The reverse, so the capacitance is directly proportional to the applied voltage, as we have earlier seen from this from the formula, and it is V naught plus VR square, and the depletion capacitance is directly proportional to the capacitance. So thus, kindly make few changes over in this line, that it's actually 1 over voltage, as the width of the capacitance is directly proportional to the applied voltage, which is root of V naught plus VR, and the depletion capacitance is indirectly proportional to the width of the capacitance. Thus, with increase in the reverse bias voltage, the width increases, however the capacitance decreases. Now if one look at the reverse recovery time, which is Ts plus Tt, that is Tt is the transition time and Ts the storage time. Okay, that's the addition there. Looking in this figure, we can see that T is the storage time and Ts is the transition time. These are the two times. The total of these two is the reverse recovery time. Now moving on the load analysis. Start with the load analysis of the diode. If you apply Kirchhoff's law to this circuit, you will see that the external voltage is equals to Vd plus Id into R. The quiescent point is that point at which you will find the biasing point to be maximum and the most stable, okay, which is dependent on the diode voltage and diode current. Okay, remember these two equations. We have already talked about these two equations. Now look at one of the 2014 GATE examination question. Now it's telling us about the Schottky diode and a normal diode. You can see that both the diodes are connected in the forward direction, but you can say that one has a potential of 0.7 and other has 0.3. I've already given you the answer, but yeah, try to solve it by yourself and you will find out that across the parallel junctions, you won't be having two different kind of voltage. We maintain a constant voltage in the parallel junction, one with the 0.7 and other with 0.3. With the one with the 0.3 will be first one to turn on. So providing a short circuit, all the current will pass through it and D1 will never get reached to its threshold voltage, and it will always remain open circuit. Now moving with the application of diode, we have talked about diode a lot and getting to know about its parameters and characteristics. Now we talk about its application. There are half wave rectifier, full wave rectifier and a bridge rectifier. Whenever you found a diode connected with a resistor, you will see that it will be a half wave rectifier. One thing I wish to tell you that there may be a lot of disturbance at this point in my video because it's raining outside and it's raining too heavily. So I try to minimize it as much as possible, but for the little inconvenience in my voice today, please don't mind that. Okay. Now moving with the application of the diode. We can see that there are two types of different diodes, not just two, there are three different rectifiers: half wave, full wave and bridge rectifier. And what these diodes actually do is they become open circuited in the forward direction, and they are closed circuited, or they become short circuited in the forward direction and open circuit in the reverse direction. So as you can see that in the forward direction, this the diode is short circuit but would have a potential of 0.7 volts across its terminal. So this amount of voltage is subtracted from the actual applied voltage Vm, which acts as the offset due to Vt, and the rest beyond T2 is 0 because it acts as open circuit to the negative part of the terminal. This is one of the basic rectifier. Now moving with the application of these rectifiers, we can see that if this is a normal diode, normal input signal, a rectifier connected a diode and an R resistor connected to the circuit makes it a rectifier. This is a half wave rectifier. It is on in the forward bias diode at the short circuit and off in the reverse bias. The VDC is 0.318 into Vm and VDC is 0.318 Vm minus Vt. For the half wave rectifier, now this is for the bridge rectifier. Bridge or full wave rectifier, or the bridge or the center tap rectifier. That means it allows both the signals, both the components of the same signal, that is from 0 to 2 and from T2 to T. Now for the signal passing from T2 to T, it not only rectifies it, makes it pass through, but also changes its phase. The signal becomes positive with VDC 0.636 of Vm. For full wave rectifier, the peak inverse voltage is 2 times of Vm. For center tap transformer having this this form D1 and D2, you can see that if a positive from plus to minus occurs, then in the positive half of this transformer, it passes through D1 and you get the voltage at plus minus V0. However, in the reverse case, it is minus and it is plus. So in the lower end, the minus and the minus of this becomes plus. It passes through plus D2 diode and through the resistor R, and there is a voltage drop at resistor R. The voltage drop at resistor R makes you, however, the D1 will be open circuited at this point of time, as shown in these both the graphs. Kindly look at the graphs and try to go through it. Now, looking at the limiter or a clipper, what does actually it means? Limiter limits or clips the input voltage to a desired output voltage, and beyond that, no more voltage will be passed through the device. Okay, so as you can see, there are various clippers, but let me look at this one, because it is the most intricate one, I feel. However, and you can get the logic about the same logic applies to every other clipper, the one that applies to this one. So if we have a input signal, an AC input signal with plus and minus Vm and a diode like this, then we can see that if suppose a positive occurs at this point and we make a conventional current direction like this, we can see that the diode will be negatively biased to the input circuit, and this will be a 0. Remember, it will be a 0 for 0 to t by 2. But however, for t to t, we will see that it's minus of Vm. With minus of Vm and plus of V, minus of Vm, there is one more thing, that is, if it is minus and this one is plus, we will say it's plus of Vm plus of V plus of V. There is a, if it's an ideal diode, there is no potential drop over it, and this will be minus of plus of V0. And by this equation, we can say that V0 is equals to, first this will be V of R. Remember it to be V of R. Okay, plus V of R. Then we again do this Kirchhoff's current law equation and try to follow it. Then it will be plus of V0 and minus of VR will be equals to V0 equals to VR, and VR is equals to minus of V minus of Vm from the initial equation, that Vm, this is minus, this is plus. Okay, then plus of Vm plus of V plus of VR equals 0. Okay, by this equation we get VR is equals to minus Vm minus V, and VR equals to V0. So V0 is equals to minus Vm minus V, which is equals to this value. So the same logic applies to every other clipper in ideal diode as well as in non-ideal diode. Remember this point, try to solve for the other logical, try to build the other logical analysis for the other clippers too. And moving forward, we look for the non-ideal diode. Non-ideal diode also works in the same direction, but this is the homework. I would like you to go through it and know it and remember it, so that it will be much easier at the time of the examination for you to recall it. Now the clamper. Earlier we have talked about clipper, and the clipper has only the resistor attached to it. But if you have a capacitor too, then it becomes a clamper. What is a clamper? Clamper actually clamps you. It's just like a heel in the device. Which clamps, which keeps the signal constant but clamps it to a positive voltage or to a negative voltage. Okay. Now the clamper, because the clamper is present, the diode could become, it will be a clipper too. It will clip some. What I mean by clipper is that it works as a rectifier. It rectifies for some voltage, but it won't clip any voltage. It will give you the maximum voltage which you have, which is there in the initial circuit only. Okay, it won't clip any input signal. So if you see this input signal and which is passed through this particular circuit, you will see that the positive voltage plus minus voltage will charge the capacitor to the plus minus voltage itself, and the diode will be short circuited at this point of time. Okay, no voltage will be there on the output because no current is passing through the resistor at this point of time. But in reverse bias condition, you will see that the diode is open circuited and the capacitor, in reverse bias condition, remember the capacitor won't change its potential direction. It will only be the input signal that will be changed its input signal direction, which will be minus and plus at this point of time, and plus and minus, and you will see that the voltage across V0 will be minus of 2V. The ripple voltage VR is equals to Vm T divided by RC, which is equals to Vm by FRC for half wave, and Vmt by RC, which is equals to 2. There will be a 2 also here for T by 2 only. Remember, it's T by 2 for full wave rectifier. Okay. Now moving on to the clamper. It works exactly the same way, but this is again your homework. Please go through it and you will see that they are easier if you get to know the logic at the first time. Now Zener diode is another application. As I have already told you, this is the anode end, this is the cathode end. Plus minus Vz is the Zener voltage across which the current will rise exponentially, but the voltage will remain constant. Okay, the Zener off state, Zener on state. Now, how to actually calculate the Zener diode is working or not? Okay, so you can see that if Zener diode is connected in the parallel, then whatever the voltage drop is across the load. Okay, that will be across the Zener diode. If it is less than the Zener diode voltage, then it is open circuit. If it is greater than the Zener diode voltage, then it is short circuit. Okay, giving the maximum voltage across this terminal will be plus Vz. Now this is the formula the theory about which I was telling to you earlier. For Zener diode, yes, we know that the VL, the load resistance the load voltage will be equal to the Zener voltage. That is the confirmed assumption. But what happens that we don't know about the current. The current can vary across the load as well as across the Zener diode. But that depends. But the current, the initial IR current remains constant. Okay. Keeping these things in mind, we have two cases: the fixed and the variable. Now in the fixed VI case, when the voltage is fixed but the load resistance varies, in that case we keep VL equals to Vz. Now earlier we have known that VL is a voltage. If you do a voltage divider, think over the load voltage, you will get voltage into RL divided by R plus RL into Vn. The RL minimum is equals to, if you say that it's a minimum, let's suppose it's given it's a minimum, okay, then we have a maximum Imax current and a minimum Zener current. Zener diode current will be minimum, and that minimum current will give you the maximum, the minimum Zener current will give you the maximum load current, and the maximum Zener current will give you the minimum load current. To calculate RL max, the maximum voltage, we have Vz divided by the IL minimum current, which is equals to IR minus IZ minimum. We keep the resistance current constant. Okay. Now the fixed RL and variable RL, same thing, same formula, same, but only the VI is different in this case. Now there are voltage multiplier, this is a doubler and this is tripler. Now if we talk about doubler, then you can see that if there is a positive voltage, then plus Vm. Okay, and this diode will be, D1 diode will be short circuited and there won't be any output voltage. However, when there is a negative voltage applied, then the diode D2 is short circuited and C2 is rise to a potential of minus 2 Vm. This minus 2 Vm, which is double of that voltage, appears with a reverse in its phase at the output. Same goes with the tripler and the quadrupler. Now, if you look at the voltage regulator, the voltage regulator is not actually the part of this diode, but considering its importance, I would like to discuss it here only. The filter voltage regulator, it is actually, when you have an RC in your circuit, you will have some ripple in your circuit, in your output voltage. So the DC voltmeter will reach the average or the DC level of the output voltage. The AC RMS meter will read only the RMS value. The ripple will be equals to ripple voltage over the DC voltage into 100. Voltage regulation is actually the no load voltage minus the full load voltage upon the full load voltage into 100. For half wave, we have already talked that VDC 0.318 Vm. For RMS, it is 0.385 Vm, which makes it as 1.21 ripple, 1.21 ripple for half wave rectifier. For full wave rectifier, it's 0.48. Thus, the ripples in full wave rectifier are much less than in comparison to the half wave rectifier. For the capacitor filter, VRMS is IDC by 4 root 3 FC and VDC is Vm minus 4.17 IDC by C. Now VDC by VR by VDC will be approximately equals to that. The small c is equals to large time is small current, small c, large time, small current, and large c, small time, large current. Okay, this is the condition that is being followed. IDC is T1 over T into IP. Since the average current drawn from the supply must equal to the average diode current during the charging period, the following relation follows, where T1 is the diode conduction period, T is equals to 1 over F. For a full wave, IDC is the average current drawn from the filter and the peak through the conducting diode. This is again the RC filter. Now discrete voltage regulation. There are two types, one is series and the other is parallel. In series, we have the control element, we have a comparator, it could be an amplifier or a limiter, anything. We have a controller element, mostly it is a BJT. BJT is a controller element, and then sampling. Sampling circuit could be a voltage divider. Mostly it's a voltage divider in our case. In parallel, we have the control elements in parallel to the comparator and the feedback, and there is an external road also across the wheel. So if you see a series voltage, as we have talked about, this is the controlling element. This is also a comparator right now. This is a comparator right now. Plus minus Vz, which compares. This is a sampling. So Vz plus VBE, Vz plus VBE is equals to Vz plus VBE2 is equal to V0 R2 upon R1 plus R2. For this we have our controlling element, our comparator, our sampling, our reference. So we have all the four parameters, and our output V0 is 1 plus R1 by R2 into Vz. We have used. Now this is 2014 question, and you can see that it's a Vz, reference, comparator, control element, and a potential divider. Okay, and the output you get with the help of Vz into Vz is equals to R upon R plus 1 into 9. And you get the value of R from there. Shunt regulator is where the control element is in parallel. Then reference, what is the comparator in this? Sampling, reference, comparator, control element. Then VL is equals to, there won't be any potential sampler in this case, I think so. Then Vz is equals to, and shunt regulator VL is equals to Vz plus VBE. And in shunt, you have the control element in parallel. Remember that control element. This is Vz, VBE, VBE2, VBE1, VBE2, Vz, and VL. There won't be any sampler as such as voltage divider, but yes, all the voltage across the load resistance will be equals to the summation of the various elements or the components present in the circuit. So with this we have come to the end of our topic. Thank you so much for being so patient and long to be with me. I would like to suggest you that GATE is not a really easy examination. It is a tough examination which tests various aspects of you. One of them is to try to solve different type of questions, but because the practice makes you important as an engineer, we cannot afford to make any calculation errors. So with this note, thank you everyone. I hope you like this video. If you like this video, kindly press the like button. Share it with other people, with other friends who are preparing for GATE, and subscribe to my channel for more videos. Thank you. Bye.